Today's video is a bit different from all the other videos that I've made before. And the reason is that the previous videos I have always focused on using the sextant's altitude to find the true altitude or the true zenith distance from it, or the resulting observed latitude and observed longitude. Today's video will be working a sextant altitude backwards, and when I say backwards, that means we'll start from the observed latitude and we'll work backwards to find the reading to set on a sextant. So basically I'll be using the example of a meridian passage question and work it backwards. So a meridian passage, if you don't know what it is, that is when the sun is exactly on the observer's celestial meridian. So that is, if I project the observer's position from the Earth's surface to the celestial sphere, when the celestial body is exactly on the observer's meridian, that is called a meridian passage. Now what happens on the ship is that at noon, which is the meridian passage time, we use the sextant to get the sextant altitude of the sun when it's exactly at its peak. But at that point of time, the sun is so bright that even though you're looking through the shades of the sextant, it sometimes hurts your eyes. So what we normally do is we kind of use the approximate latitude, which we call the DR, or the dead reckoning latitude, and we work it backwards to get an approximate sextant altitude, which we can then set on the sextant and then look towards the horizon. So the sun, then you don't have to look directly at the sun when it's at its peak and bring it all the way down from its positions to the horizon. You can actually adjust your shades in such a way that you will see the reflection or the reflected sun on the horizon somewhere, and then just adjust your sextant to get its altitude at the time of the meridian passage. Alright, so this is all about finding the reading to set on a sextant, so working a meridian passage question backwards. So hopefully, if you have not understood what I said so far, hopefully the question itself will be clear when I work out the question for you. Alright, so the question says find the reading to set on a sextant with 1 minute index error of the arc. So the sextant error is 1 minute of the arc, and then you have to observe a meridian altitude of the sun's lower limb, alright, on 4th of July 1992. So the keywords here are the index error, then it's the sun's lower limb, and the date is 4th of July 92. The DR lat, or the dead reckoning lat, or it's also known as the estimated lat and long, is given to you, and the height of I was 7.7 meters. So the height of I is given to you as well. Alright, so what you have to find is what reading will you set on the sextant at the time of the sun's meridian passage, lower limb. Alright, so to do so, and today again the way I will solve this question is a bit different. Normally I solve the question and then take you through it. Today I'll be solving the question along with you so that you can see what's happening here, because I'm working backwards. So hopefully that will be helpful to you as well. Alright, so the first thing that you do is basically find out the LMT meridian passage for 4th of July. This is normally what we do. So this is not different yet. So even if it was a meridian passage question, the first thing that we do is normally find out the meridian passage time at which the Marpas will occur, or the meridian passage will occur on 4th of July. Alright, so let's go into the nautical almanac of 1992 for 4th of July and find out what time is the meridian passage going to occur. So you can see that this is the 1992 almanac, and this is 4th of July is somewhere here. The sun's meridian passage is given here in the right hand corner. Alright, so if you see this column here, this is the meridian passage column. It says Marpas. 4th of July is here, and the meridian passage time is 12:04. Alright, so that's the local mean time of the meridian passage. That's not the GMT time. Normally, the time given to you in the almanac for which you find out the GHA and the rest of the stuff for declination is GMT, but these times on this side here is your local mean time, LMT, and that's your LMT meridian passage for 4th of July is 12:04. Alright, To that LMT, if you want to find out the GMT of the meridian passage, and why do we need to find out the GMTs? Because for the rest of the question, or to find out the declination of the sun or anything else, you need to find out the GMT. The almanac is gives you values for the GMT time. All right. So we apply a correction called the LIT. The LIT is also known as longitude in time, and the LIT correction can be calculated by dividing the dr long by 15. So the date reckoning long is given to you, or longitude is given to you as 165 degrees. Just divided by 15, you will get exactly 11 hours, 0 minutes and 0 seconds. Because it's east longitude, when longitude is east, GMT is least. That means GMT is behind you. So if your ship is in east longitude, the time on your ship will be more than the time at GMT. So the local mean time on your ship will be more than the GMT time somewhere around UK. Alright, so as you move east, you add hours. So that's why your local mean time is more in the east longitude than comparison to the GMT. So that's why you will subtract the 11-hour correction of LIT and you get the GMT meridian passage. Alright, now all you have to figure out is whether the date is the same or not. So if this was 4th of July was 12 hours, 0 minutes, 04 minutes and 00 seconds. If I subtract 11 hours, is still the same day at GMT? Yes, it is. So although we are 11 hours ahead of GMT, the GMT date is still the same. It's 4th of July. It's early morning 1 o'clock at GMT. Alright. So that's why your GMT meridian passage time for 4th of July is 01 hours, 04 minutes and 00 seconds. Alright. After that, you still work the question normally as you would and find out the declination of the sun. The declination of the sun you find out by going back to the nautical almanac for 4th of July and 1992 almanac I'll be using, and for 01 hours you find out the declination value. At the bottom of that column, which I'll show you very soon, the D value will be given. I'll show that to you as well. And the next thing that you have to actually observe is whether your declination is increasing or decreasing when you go from 01 hours to 02 hours. Alright, so this is what we'll be doing. We'll go back into the nautical almanac for 4th of July 1992. So again, I've come back to the nautical almanac for 4th of July 1992, and for 01 hours, let's find the declination. Alright, so this is 4th of July here. Right, 01 hours is somewhere here, sun is somewhere here. All right, this is the GHA and the declination column. You don't need the GHA for this question, so the declination column is here. For 01 hours, you can see the declination is 22 degrees 52.2 minutes north, and you can see that the declination is reducing to the next hour. So the D correction that we'll find for a D value of 0.2 from here at the bottom of the column here should be subtracted, because declination is reducing from 01 hours to 02 hours. Alright, you can pause the video here if you want to, if you didn't understand how I found these values, but otherwise it's pretty straightforward, and you can watch all my other videos as well to find out how do we go into nautical almanac and find out the values for declination. Alright, so I'll go back into the solution. So this is where I found out the declination value from for 01 hours, the D value for 0.2, and then I said I will subtract the correction once I found out the correction for D value. So to find out the correction for the D value of 0.2, you have to go into the increment section for 04 minutes and find out what's the D correction for it. Alright, so we'll go back into the nautical almanac again. So we'll go back into the nautical almanac for 04 minutes of somewhere here is 04 minutes, and you can see here this column here gives you the V or D correction. So for 0.2, which is here, the D correction is 0, so it doesn't matter whether you subtract or add, you will get 0 out of it. Right, so I go back, and that's why you have the 0 here for correction. So the declination remains the same for 01 hours, 04 minutes and 0 seconds, 22 degrees 52.2 north. Alright, now from here onwards, the solution or the way you solve the question changes. Because normally, if you have seen all my other videos or if you are familiar with working a sextant altitude, we go from top to bottom, right? We go from top to bottom. But today, we'll do something different and we'll go from bottom to top. That's right. All right. So we'll start right from the bottom and then we'll use the rules that we normally use while going from top to bottom to find out the values while going towards the top. All right. So let's start at the bottom. So normally what we do is we resolve the sextant altitude which is given to us in the question, or which we find through our sextant observations, and then find out the observed latitude towards the end. But today we'll start from the latitude. Of course, it's not the observed latitude, it's a dead reckoning latitude. That means it's the estimated latitude, it's not an accurate latitude, but we'll use that as an approximate latitude to find out the approximate sextant altitude to set on a sextant. So the latitude given to us is 40 degrees 20 minutes north, so we'll just put that here, 40 degrees and 20 minutes north. Alright, then the next row is the declination. Just put the declination you found out is 22 degrees 52.2 minutes north. So put down the declination as 22 degrees 52.2 minutes north. Alright, the reason I'm doing this question with you guys is so that you know what's happening here. Otherwise, if I had resolved the question beforehand, I was not very sure whether you guys will understand what I've done or not. Alright, so anyhow. So now you've got two values. Now you have to find out the mzx. The mzx stands for your meridional zenith distance. That means it's your angular distance or the observer's angular distance from the celestial body when you are projected into the celestial sphere. Alright, and this meridional zenith distance refers to the angular zenith distance of the body from you as an observer during the meridian passage. That's why it's called meridional zenith distance. Otherwise, it's called true zenith distance. Alright, so basically, if you can visualize it on the celestial sphere, your meridian and the sun's meridian is the same. Alright, but let's figure out where you are bearing from one another. We'll do that later on. Let's get the value of the mzx first. Alright, so to get the value of mzx, we have to think about how we would have worked this question if we were working from top to bottom. So here, this is the rule that if the meridional zenith distance or mzx and the declination were opposite names, you would have subtracted them. So that means if they were south and north, you would have subtracted them, and then the latitude would have retained the name of the larger. Whatever would have been the larger, the latitude would have been named that. But if they were same names, you would have added it. Right? So now you have to figure out your mzx, would it be north or would it be south? Now let's assume if it was south, then the mzx and declination would become opposite names. That means you would have to subtract it, right? So if you had to subtract it, the mzx value would be somewhere close to, let's say, 62 or 63 degrees, because subtracting it from 22 would give you about 40 degrees. But then mzx would be south, and then you said that the latitude should be retained, or latitude should retain the name of the larger. Then the latitude would have become south here, right? But we know for a fact that we are not in the south latitude, we are in north latitude. So this cannot be right. So we'll erase it. We'll erase this. We'll erase this. So this cannot be south, right? Because we know for a fact that we are in north latitude. So that means mzx has to be north. And if I say that the opposite names are subtracted, then the same names should be added. So if I add the same names to find out what should be the value, we'll just subtract 40 degrees 20 minutes minus 22 degrees 52.2 minutes, and that would give us 17 degrees 27.8. Alright, so how do I find that out? I subtracted the latitude minus the declination. Right, for now I'll erase this line. I'll come back to this line later on. That's how I found out the value. Alright, so now if you add the mzx and declination, which are the same names, and the rule says the same names should be added, you will get the latitude as 40 degrees 20 minutes, and then you can name it north because both of them are north, so it doesn't matter. Alright, now if you are working a question from top to down, you would have subtracted true altitude from 90 degrees to get mzx. But since you are working from bottom to down, you do the same thing. You actually subtract mzx from 90 degrees. Alright, So what am I trying to say here? That if 90 degrees minus true altitude, which is the normal case normally, gives you mzx, then if you take true altitude onto the other side, 90 degrees minus mzx will give you the true altitude. Yes, if it goes here and this one goes here. So that's what we'll be doing. To get the true altitude, I'll be subtracting 90 degrees minus the mzx of 17 degrees 27.8 minutes, and I get 72 degrees 32.2 minutes. Alright, 72 degrees 32.2 minutes. Now here you are supposed to name same as bearing. I'll tell you what this means, although here it doesn't hold any significance, but I'll still tell you what this means. How can you name the true altitude? Alright, then you get the concept of the bearing as well. Alright, so just before I do that, let me just write down how I got my true altitude. The true altitude here was 90 degrees minus mzx. Of course, you know that, right? I've written that before, just to be clear. Alright, so you can pause these videos here and then make a note of what I have done, because I'll be erasing all this writing, otherwise it's getting too cluttered. So I'll erase all this writing here, because now you know how I've been getting these values. Otherwise just go back onto the video and watch it again, because if it gets too cluttered, then it just gets very untidy and you won't understand what's going on. Alright, so we'll come back to the point I was talking about. How do you name your true altitude? And it says name same as bearing. So that basically means that you assume that your position on the Earth's surface has been projected onto the celestial sphere. And now, of course, during the meridian passage, the sun's meridian passage, or the sun's sun and you are in the same meridian, because it's exactly on top of you, right? So what you do is basically you assume that you draw a Q which stands for the celestial equator, and the celestial equator is also called equinoctial. Alright, this is celestial. This becomes a reference point. And then you draw your position, which is the observer's position, which is the latitude. And it's 40 degrees 20 minutes north, so you go north of, sorry about that, you go north of the equator, of course, just like you would on the Earth's surface. And you call yourself Z. This stands for observer's zenith. That is your position projected from the Earth's surface to the celestial sphere. And now you draw the sun. The sun latitude is the declination. Right? So this ZQ becomes latitude, 40 degrees 20 minutes north, and XQ or QX, the celestial body is denoted by X. Alright, this becomes the sun, and the declination is 22 degrees 52.2, so this distance here becomes declination. So now you see that the body is bearing south of you. So the body is bearing south of you. So if you were also in the celestial sphere roaming around, and the celestial body is in the celestial sphere, the celestial body will be bearing south of you, and that's how you name the true altitude. You can name it south here. Although in this question it's not relevant. If you were working it from top to bottom, then it would have been relevant to name your resulting mzx and then and then to, of course, resulting mzx. All right, because the mzx is named opposite to true altitude, as it says over here. All right. So this has no relevance here, still I showed it to you. Alright, now we find the total correction. So the total correction is normally found for the apparent altitude value. The app altitude that you see here stands for apparent altitude. But today, because we are working it backwards, you will assume that the true altitude gives you the apparent altitude's value. And using that as an approximate apparent altitude value for the sun's lower limb for the month of July, because that's when your site was taken, 4th of July, you will find out the total correction value for 72 degrees 32.2 minutes. So you have to go back into the almanac, and normally in the almanac it's the third or the fourth page, but here the digitally arranged almanac I've changed it a little bit, so that's why here it's towards the end. So this is the page that you have to go into. This page here gives you the height of eye, that is called the dip, and the total correction for sun. And depends on the month. So if it's October to March, it's here. If it's April to September, it's here. So you have to find for July, which stands here. So July comes between April to September, so you'll go here, and the apparent altitude value, we'll assume that the true altitude is the apparent altitude for 72 degrees 32.2. You go down this column, and somewhere between 67.15 and 73.14 is the value. you have to find for upper limb, and that is a negative correction of minus 16.2. So you take that correction and go back into your solution and put that minus 16.2 here. Alright, so since you are subtracting, isn't it upper limb? Oh, it's lower limb, I'm sorry, it's lower limb, and I'm confusing. So it's not upper limb, it's lower limb. So my apologies. I will go back into that table and find out the lower limb correction. I confused myself. So the lower limb correction here, I'll erase this, is plus 15.6. Okay, so if you are wondering how I know this, so at the top of the column you can see this is lower limb and this is upper limb. So the lower limb corrections are always positive and the upper limb corrections are negative. So it's plus 15.6. Alright, so I'll go back and I will write plus 15.6 here. Alright. So if I'm adding plus 15.6 while coming from top to bottom, when I'm going from bottom to up, I should be doing the opposite. So although the correction here says plus, I will actually be subtracting it. So you will get why. So what I'll do is I'll subtract 72 degrees 32.2 minutes minus 15.6 minutes. This is only minutes. So when you subtract it, you get 72 degrees 32.2 minutes, and then minus it with 0 degrees 15.6 minutes in your calculator. You get 72 degrees 16.6 minutes. Right, so if you didn't understand what I did there, although it was showing a positive sign, why did I subtract? But now if you look at it, you will get the idea, right? So if it was working from top to bottom, you would have to add this correction, right? So only if you added this correction, you would get the true altitude of 72 32.2. But when you are working from bottom to up, you have to do the opposite of what the correction tells you. Only then you will get the resultant. Right? So if you look now, it makes sense. So if you had added this correction, it wouldn't have made sense to you. Alright? Then you find out your dip correction, which is your height of eye. Now height of eye given to you is 7.7 meters. So you find out the height of eye correction for 7.7 meters. So you go back into the table from where you found out your total correction. And over here is your height of eye for 7.7 meters. And this here says height of eye. This is in meters. This is in feet. 7.7 meters is somewhere between 7.5 and 7.9. No interpolation required. You just take this correction of minus 4.9 and put it back into the calculation there. So minus 4.9 is your height of eye correction. And again, like I said, the sign, whatever the sign says, you have to do the opposite now while we are working from bottom to down, bottom to up. Alright. So because the sign says negative, you will add to it. Alright. So you add 4.9 minutes to 72 degrees 16.6 minutes. And what would that give you? 21.5. So you get 72 degrees 21.5 minutes. See, now it will make sense. If you go from top to bottom, if you subtract it, that's what your apparent altitude will be, right? So if I draw a line here, I should be drawing a line here. So that's how it all works. Alright, and now the final correction, index error given to us is, 1 minute index error of the arc, right? So just apply 1 minute index error of the arc. So whenever it's off the arc, we always add our index error. If it's on the arc, we subtract our index error. Alright, so because this says a plus sign, you will be doing the opposite. You will subtract 1 minute. So what will you get? You get 72 degrees 20.5 minutes. Right? So now if it will make sense if you look. So from just you can do a cross check, start working this question from top to down and see if you have applied the corrections correctly or not. So if you see from top to down, if I had index error of 1 off the arc, 1 minute off the arc, I would be adding it. So if I add it, I am getting 21.5, makes sense. Then I will subtract the height of eye correction. Height of eye is always subtracted. So 4.9, I'll get 16.6, which is correct. Then the total correction of lower limb is plus 15.6, makes sense again. 72, 32.2. Then I'll be taking it off 90 degrees to get MZX. And I'll be getting 1727.8, and then finally of course I'll apply the rules and get the latitude. Alright, so your approximate altitude to set on the sextant will be 72 degrees 20.5 minutes. So I hope this question was a bit different and a bit interesting for you, because it requires you to think a bit differently from how you have been thinking so far. If it was not very clear to you, or if you have any doubts, please write to me in the comments, and I'm happy to get your feedback. And you can suggest some topics that you want me to cover. I thought this was a different kind of a topic, so I covered it for you guys. Hope this video helps. I'll be putting up another video soon. All